Hey guys, welcome to my channel, Math for Teens, and also welcome to this new series where I'm going to be exploring Taylor series under many facets, dimensions. So this video in particular is going to be an introductory video to Taylor series. I'll explain what it is, and also I'll do a derivation of its formula. But this derivation will assume the properties of a Taylor series to begin with, and from there we'll derive its formula. I'll also make a video on deriving the Taylor series just as an expansion almost from the fundamental theorem of calculus and integration by parts. And then a third type of derivation proof that I'm going to do of just deriving the Taylor series formula is going to be centered around assuming a polynomial function. And this is the last one I'm really excited for because I think it involves a lot of high tier math. So basically, I'm just going to assume a function, a polynomial function that is kind of approximating another function, and I calculate the area, which is the difference between the two functions. This is an integral. And then we use a method that you would use in kind of neural networks when you're trying to minimize area. We use mean squared error, which is just a measure of how far off our polynomial function is. And anyways, we'll go all about kind of weighing that error and minimizing it. So that'll be a really cool video. It will involve I think a lot of top tier math. I'm not there yet. But yeah, that's this video, and later on in the series, we'll also just explore some applications of Taylor's series. I mean, the obvious one is Euler's formula. Another one is Euler's kind of derivation of, or his proof of the sum, I think, of the inverse of squares, I think. I think that's what it is, at least. 1 plus, a quarter plus a ninth. I think you go into infinity, and it's ooh, maybe don't quote me on this, but pi squared over 6. It's something unexpected. He found it using Taylor's series. Okay, so I've done enough talking for now, so let's get into the video. Okay, so first things first, let's back you guys up or bring the camera up. So solution. So we're going to be looking at Taylor series as I've said. What is a Taylor series? Okay, so a Taylor series is an infinite series of polynomial terms, right? So think of f of x is equal to a0, right? That's the 0th power, and each term increases in its degree, if that is making sense to you guys. So you'd have a0 plus a1x plus a2x squared plus a3x cubed, right? So we're getting higher and higher degrees of x, each with their own unique coefficients, all the way until the nth coefficient and the nth degree of x. Okay, so this is generally what we consider just a polynomial series. If it goes on forever, it's an infinite number of terms. It is, I guess, an infinite polynomial series. And that is the case for the Taylor series. Now, what is specifically unique and special about the Taylor series? Well, the thing with the Taylor series is that it's used to approximate a function around one point, really. So say we had f of x equals e to the x, right? And I somehow want to approximate this, not with e to the x. I think it's an exponential function here, obviously. I don't know why I'm saying transcendental, but clearly there's a difference between exponential functions and polynomial functions. So really what we can achieve here is an approximation. But we'll get a pretty good approximation around, say we're trying to approximate e to the x around, x equals 0. we'll get a pretty good approximation for points around 0, and eventually the two will diverge, right? So this might be our Taylor series. The points around our expansion point, x equals 0, they will be near identical. And as we drift further and further off from our expansion point, the two will differ. What does it mean though for functions to be identical? Like think of the Taylor series as kind of a copycat. It's trying to literally copy a function around a point. But what does that really mean? What does it mean to copy a function? Well, you're copying a function's characteristics. You're copying its behavior. And I've seen different people refer to this as a function's kind of DNA. What is a function's DNA? Well, what do you have? What does a function actually have? It has a value. There's f of x, right? It has a slope, right? The slope of the tangent line at that point. It has a second derivative. You can see over space, how is that slope changing, right? Is it getting bigger, smaller, right? So there's a second derivative. It has a third derivative. We see, how quickly are those changes happening. So yeah, that's kind of what we have right now. You can go all the way until the nth derivative, fn of x. And these will all give you a pretty good idea of how it's behaving. Like, for example, think about if f of x is the population of a bacteria over time. So f of x is the population at a certain moment. What is f prime of x? Well, that would be simply, you'd have a slope of a tangent line here. If this is, what is a slope? A slope is rise over run. Rise over run. What is rise? It's the difference between two y points. The difference between two y points here is a difference in population. So we're talking about variation in population over time, right? So our first derivative here kind of represents the speed at which the population is either growing or decaying, right? We could say it grows by 50 or 50,000 bacteria per hour. Guys, don't hate on the extreme example. I don't know, but that is the speed of growth. Second derivative, it tells you how quickly are these changes in growth actually happening, right? So it's kind of, each different point will have a different derivative. Or it's not saying how quickly, but it's 2 points will have a different derivative. And I think it's telling you kind of how much is the derivative changing per moment in time. And think of it like acceleration. So I guess it's the speed at which the changes are occurring, if that kind of makes sense, maybe. But yeah, I feel like I need a better way of formulating that. I need to be able to visualize it clearer myself. Well, you can just kind of think of it as, what is the difference between these slopes, and over what time does that difference occur? And you see on every moment how much is the slope changing, I guess. That would be your second derivative. And you can kind of expand this idea behind all derivatives. They kind of describe the previous derivatives. But in the end, you're describing some really complex behavior of a function, right? You're describing what it is at a point, how it's changing. I know what it was like before the function. I know what it was like before this point. I know what it's like at that point. I know how it will be changing in the future. I kind of have a good mental image of a function. And once again, my Taylor series, it's going to be copying that mental image. So if I can get the same value at that point, of like that expansion point, whoa, just thunder. If I can have the same derivative, same second derivative, same third derivative, I will have copied the function around this expansion point. I will have copied its DNA. Okay, so that is the purpose of the Taylor series. So what we've just said is that, well, let's call this P of x, and e to the x will be f of x, right? Basically, we're saying that f of x at our expansion point will be equal to P of x, f prime of x will be equal to P prime of x, f second derivative of x will be equal to, you guys see the P. Yeah. So the nth derivative of P will be the nth derivative of x. Okay. I feel unsatisfied with my answers for you guys on just the general derivative section. So what is okay, so yeah, the first derivative is the rate of change, so speed or slope. The second derivative tells you the rate of change. It tells you how the rate of change, which is your derivative, how it's changing. So we call that usually acceleration. And then third derivative tells you how the acceleration is changing. Yeah. I mean, it's easy to see from a kind of curvature perspective. Like if slopes are getting smaller, they're approaching zero, you're gonna have concavity downwards, right? Yeah. What else can I say? I mean, this is its own video, honestly. But understanding the general idea behind is a good idea. Where was I? Okay, so I just set some criteria for our unknown polynomial series. Now, what we actually need to identify in this video, so that we can actually get to a Taylor series, because right now we just have a generic polynomial series, we need to identify all of these coefficients, right? If we can we're assuming that this polynomial function will be able to accurately describe the behavior of f of x around an expansion point x if it can satisfy these criteria. And with this, we're assuming that we can find the coefficients that will be able to, accomplish this. Okay. So why don't we now, I'm gonna erase this. For simplicity's sake, let's choose our expansion point to be 0. Let's choose to approximate the function around 0. The reason I'm doing this is because it makes it a lot easier to cancel out terms. If terms have an x in them, you know they'll be equal to 0. Because at this point in the video, our tactic is to isolate coefficients one at a time to find some sort of relation that we can find, some sort of way of knowing what they might be beyond just a variable. Okay, and so us expanding around x equals 0 allows us to easily knock out other coefficients that we're not trying to isolate at the moment. Now the other thing is, well, how do we ensure, well, this here has an x, how do I ever isolate that? And now there's the handiness of it being a polynomial series. Its derivative always knocks down a power or a degree from your x term, right? So let's do this. Let's do this one at a time. So we're saying that if I'm saying that p of 0, right, equals, we'll replace all of these with all of these x's with 0, so we'll just get p of 0 equals a of 0. Okay, so I guess that's good to know. So I will be able to replace, and I know that p of 0 equals f of x, right? So I know that a of 0, or a0, is just f of x. That is the first term in my series. Yeah. Okay. Now the next thing is that p prime of x equals all of this prime. So what's the derivative of a constant? It's 0, right? The derivative of this it's x to the 1 minus 1, that's x to the 0. So it's just plus a1. I'm just going to assume you guys know the power rule, so we'll get on with it a bit more smoothly, right? Plus 3a3x squared plus n a, I'll write that normally, plus n a n x to the n minus 1, right? This is just us using the power rule. And because we chose our expansion point to be 0, I think very, very smart of us. I also think when the expansion point is 0, you call it a Maclaurin series. But anyways, when our expansion point is 0, so p prime of 0, all of these will cancel and just get a1. Okay, so what have I just determined? I've determined that a1, the coefficient of this term, is equal to f prime of x. Okay, this is it's interesting. I wanted to approximate a function and suddenly I'm getting derivatives as my coefficients. How far does this actually go? So let's see. When I do the second derivative, the second derivative of x is equal to, or I'll say 0 because I'm not trying to do 2 lines for each one of them, but this x will disappear, we'll get 2a2. And it doesn't really, well, okay, I'll write that, I guess. So plus 3 times 2a3 to the times 0, that would be x. And then plus n times n minus 1 times an to the times x to the n minus 2, right? So, obviously, sorry, this is a 0. So obviously I know that these terms are going to 0, so I just have that second derivative at 0 is equal to 2a2. So what do I have? I have a2 is equal to second derivative of x divided by 2. Okay, I'm going to do the third term so we can see kind of pattern going on. But what I want you guys to just take note of is that, once again, this being a polynomial series, every time we do a derivative, what happens? We kind of get a degree that falls down each time, and each degree is one less than the other. So we have 3 times 2. Let's say this was how do I say this? Let's say this was a4, x to the 4. We'd have 4 times 3. Well, I'm not going to spoil it, but how do I say this? The pattern that this is making, with just it being the power series, you're going to have powers dropping. So, 5, next derivative will be 4, next derivative will be 3, all the way until 1. And what we call that is a factorial. So let's do another one. So my third derivative at 0, what's that? Well, this x is just going to disappear, right? So we get 3 times 2 times 1a to the 3. And then this also includes x, so we're just going to ignore it for now. But what do I have? I have that a3 is equal to the third derivative of x divided by 3 times 2 times 1, which is just 3 factorial. So what is the pattern here exactly? Well, I have that a to the n is equal to f to the n of x, the nth derivative of x, divided by n factorial. That is the pattern that I have found. And so now, what can I really do now? I'm going to, hold up, sorry. Okay. Just gonna erase a lot of this. And why exactly is the Taylor series an infinite series? Well, I think just the notion of it being an infinite series is that we'll never exactly converge to the function is trying to copy. But if we keep adding terms, it'll just keep on approximating it better. So, yeah. Now there is an error term in the Taylor series, which is not really accessible in this derivation, but that's why I'm going to be doing a little bit more complicated derivation in the next video. Okay, so how can I write out this Taylor series? Once again, just if you guys are maybe having a bit of doubts in your mind at this point, what we just did is we have found a rule for the coefficients of a polynomial series. The way we found these coefficients is we've assumed that it has the same value and the same derivatives around a certain point. And that is just so that we can ensure that it is copying that function around that point. It encodes all of the same DNA, basically, of the function. Because what else can you really know about a function besides its value and how it's changing? If we can copy that, we've copied the function. So now, my Taylor series, we have, we'll just say p of x is equal to, what do we say? Oh, wow. Well, a to 0. A to the 0, that would just be f0 of x. Divided by 0 factorial. So that was just f of x in this case. So with f of x plus a1, that is, oh wait, I did mess this up a bit. Yeah. This formulation is not quite there. Because for a1, it should be, well, no, a to the first derivative, yeah. But as long as you guys understand that that's what I'm meaning. Right? So we have f prime of x, first derivative. I guess the 0th derivative just mean f of x, like, I don't know. But anyways, f prime of x times x, right? Let's not forget that it's still a polynomial series. This is still a coefficient, even though it's a derivative. Divided by 1 factorial, so no need to include that. Plus, what's a2? Second derivative of x times x squared divided by 2 factorial plus third derivative of x times x cubed divided by 3 factorial. Okay. What's the last thing that I wanted to note? You will sometimes see a Taylor series with, I'll just add a final term, right? Plus f to the n of x, x to the n on n factorial. This can also be written as the sum from n equals 0 for Taylor series is to infinity, right? And then once again, a to the n, so f n of x divided by n factorial times x to the n. However, we will usually see x minus a to the n just to represent where a is your expansion point. So I'm gonna actually do a little bit of research firsthand right now, just to sort this out, kind of. So, yeah, so we would call this a Maclaurin series because we were expanding around x equals 0. That's the point we were wanting to match our functions up at. Okay. Yeah, so this, yeah, okay. Maclaurin series formula. Just want to make sure that this is actually what you would refer to as the Maclaurin series formula. Well, of course, the one difference is that, so for the correct notation for this is, because our expansion point is around x equals 0, my derivatives are calculated at that point. They're supposed to match at that point. And then the other x's, they're not 0. We're not just writing the value of a function at a single point. We're still representing an entire curve. But the way that the values at the way that that function will be calculated at different values, different x values along that curve, is still a result of the derivatives and the value at our expansion point, if that makes any sense. So our Taylor series, it quite literally revolves around that expansion point. Values at other terms are determined by just the fact that the expansion series and the function we're copying have to match. Yeah. For Taylor series, it is a similar idea. It's just that, once again, we're always making sure that, well, the whole idea of finding our coefficients here was that we're looking at a certain point and we want the derivatives of both functions to match and their values to match. That certain point is what we would call A. So I would have, I guess I'll write it in just summation notation. So from n equals 0 to infinity, we would want all of our derivatives at A to match, including just, so the fact that those derivatives would match is how we found our coefficients. And then subsequent values would be subsequent values of the function are calculated kind of around our expansion point. The expansion point is the center. So if I had my exponential function, but instead of this being my expansion point, if this was A over here. And so I need the derivatives to match here, second derivatives, all of that. And then the way I would calculate values of f of x, my Taylor series, near A, would be as A being the center, as my expansion point. So I would calculate my x, it would become x minus A, right? So, example, if A is 3 and I want to know what is x at as 4, well, I'm really saying one step away from A. What will f of x be? Okay. Trying to see if I myself have any questions that I want to ask at this point. And I want a clear answer. I want to make sure I'm not giving you guys any BS or anything. So, right? Okay. So, I think that the Maclaurin series was probably easier for us to understand because we're the ones who actually calculated it in this example. So it's it makes more sense to us. Oh my god, did you guys see any of that top? Hopefully. But for me personally, the Maclaurin series is a bit more accessible in this derivation because we expanded around 0, right? And so when we're actually writing out the Taylor series, we're generalizing the results we found. That's why it might seem a bit like I need some more proof, I guess. Maybe that's just me. But, okay. Okay. Yeah, so I'm just kind of going off. I asked the question to Gemini. Just so the derivative, once again, all the derivatives have to match at a certain expansion point, and that's kind of all the Taylor series is founded on. A Taylor series doesn't have to know the behavior of the function everywhere. It just needs to know it at the expansion point, so it can give good values of f of x around the expansion point. And those values around the expansion point, well, they depend on, what do we say? On the derivative, on the second derivative, on the third derivative of that expansion point, right? Because those quite literally say, how's my slope changing? It tells you how the function will be changing in further steps, right? So it makes sense that I need to know from my center point A, I calculate its derivatives there on what's going to happen at nearby points, what's the concavity going to be, what's the derivative going to be, and those future points centered around A, so x minus A, well, they will give me, they will be calculated as a result of these derivatives. That makes sense, I think, but okay. Okay, yeah, I think that makes sense for me at this point. And if it doesn't, maybe rewatch the video, because I think the step process of finding out the coefficients, it makes clear sense as you do it, right? It's not a complicated idea. It's just that the behavior of the functions need to match at an expansion point. And literally just with that, we can find the coefficients. Yeah. So this is the first, I guess, derivation of the Taylor series. Sorry, I've been kind of talking a lot. This is also like, I'm teaching myself through you guys at this point, because I did finish calculus in high school, but as you can see, it's important to ask yourself questions, and that's the only way to learn, so I guess that's what we're doing. So this is the Maclaurin series. This is the Taylor series. We just said the only difference is that Maclaurin series A is specifically set to 0, where A is the expansion point. But I'm not quite done this video. I thought I was, but I just realized I should give you guys an example, right? Because I'm not going to say every function, but functions that are differentiable everywhere generally have a Taylor series. That means that there is an infinite series of polynomial terms that can approximate it pretty well around a point, right? Around a center point that you can choose. And for the sake of this video, let's just go with Maclaurin series, right? They're clean, they're easy. It's just, x. This is 0, right? Expansion point. Okay. So let's do what we set out to do. Let's find the Maclaurin series of e to the x. So how do I want to do this right now? Should I raise the top and see what goes? Okay. Yeah, my phone just turned off again. Okay, so what we just set out to do is find the Maclaurin series of e to the x. So, I kind of have the blueprint here. So I said that my first term, a0, is just f of 0, right? I'm basically looking at e to the x. I'm saying I want a polynomial series that will match at x equals 0, right? I want something like that. And then eventually it will go a bit off, awry. Okay, that was not really, this doesn't look like a good approximation, but this is how the function will act. So my constant term is just f of 0. E to the 0 is 1. So I'm saying that e to the x is equal to 1 plus, and one last thing. The thing with this being an infinite series, I think it's what allows you to actually use an equal sign, I believe, because the series never ends. We're always adding terms, which means if we had infinite time, they would technically, the error term would go to 0, I guess. It's just we don't have infinite time, right? So f prime of x is f prime of 0, right? Well, I mean, f prime of e to the x, the derivative of e to the x is always e to the x. If you're always taking the derivative of 0 because it's our expansion point, then you're always just going to get 1. So all these coefficients are 1, so we have 1 plus x squared on 2 factorial plus x cubed on 3 factorial plus x4 on 4 factorial plus x to the n on n factorial. Okay. And yeah, that's kind of, let's check Maclaurin series of e to the x. I think it might just be as simple as that. It is. And you guys have one less shadow of doubt with this, these zeros here. It's once again, the way we found our coefficients was through the process of isolating them with differentiation. So we would literally, and differentiation around 0, so that all of the terms would disappear. And then we would have that the derivative at 0. We have to say derivative of 0 because we're setting x to 0. That's the only way that all the other terms disappear. So the derivative at 0, then we can isolate our coefficient. And that's why all the coefficients have the nth derivatives of 0 in them. Okay. Yeah, so this is the Maclaurin series of e to the x, and I think that I will leave it at that for today's video. Thank you so much for watching. I hope this video helped a little bit. I know it's not the most formal video, but I hope it encourages you to ask questions and not just learn things out of blunt memorization. For me, I would say this video has made me curious about, I think I should look more into just making sure my logical definition of nth derivatives is more solid, like how they build on each other. And paying attention to the steps, like this 0 is extremely important. Having x or 0 there completely changes the sense of the function. But I think for me, I've rethought about it. It makes sense. But yeah, thank you so much for watching, and I hope you have a good rest of your day.